In last class, we have discussed the notion of differential equation. To be more precise, ordinary differential equation. And we see that it's an equation containing of the independent variable, dependent variable, okay, and its derivative. Okay, so observing that all in a nutshell, we can generalize the nth order differential equation in the following way. Okay, so in general, nth order ordinary differential equation can be denoted by, okay, we know that at one side there is this expression containing x, y, its first derivative, and it goes on till nth derivative. So I can write down it as sum in mathematical form, just some function of x, y, first derivative, second derivative, and this goes on till nth derivative. And there can be a constant which can be put in this f itself equal to 0, and say let x belongs to say some interval j, where this j is any open interval or closed interval, or it can be a semi open, semi closed also, okay, where this y is unknown. Okay, now in this expression, in this general way of ordinary differential equation, our main aim is to find that distance, is to find that unknown function, or is to find that dependent variable which satisfies the given differential equation. Okay, and that is what is called as the solution to the ordinary differential equation. Okay, now most of the time we don't get it as an explicit function. It can be an expression consisting of y, x, y, the dependent variable, and the independent variable x, and it will be free from any differential coefficient. Okay, so it is basically a function functional relation, I can say, between the dependent variable y, in this case we use y, and an independent variable x, that is defined in some interval, g. Okay, and satisfies the given ordinary differential equation, is said to be solution to the given differential equation, or solution of the differential equation, solution to the given ordinary differential equation. Okay, so that's how we define the solution to the given ordinary differential equation. Okay, let's discuss couple of examples. Okay, examples. Let me take the first one. Verify phi of x, the given function phi of x. More often it is denoted as y itself, but to show you the difference between the given function and the dependent variable used in the differential equation, I use this phi of x equal to e raised to k x is a solution to the differential equation y dash, that is dy by dx, is equal to k time y. This is a simple first order differential equation. Okay, now basically when this can be a solution to this differential equation, first thing, this phi should be defined for the values for those values of x where this given differential equation have solution. Secondly, it should be differentiable, as y dash is involved, this phi should be differentiable, and at last it has to satisfy the given differential equation. Okay, now we will directly check whether this given phi, because we assume that the way it is defined, it take care of every other parameter, so we will directly see whether this given phi satisfies the given differential equation. What do you mean by saying phi satisfies the differential equation? Phi should satisfy the value of should satisfy the role of y over here. That means I should prove that phi dash of phi, that means I need to check that phi dash of x is same as k into phi of x. Just replace y by phi. This is what we need to check. Okay, so now to check this, what we will do is that we will differentiate phi. Okay, so what is your phi? Phi is e raised to kx, exponential function, so its derivative is k time e raised to kx. Okay, and this is basically same as k time e raised to kx is same as phi of x. So we see that phi dash is same as k time phi, and this is which satisfies this differential equation, and so I can say that phi is solution to y dash is equal to ky. So this is simple first order differential equation. Let's take a one more example of a second order differential equation. Okay, verify. This is a very famous, very popular differential equation used in mathematics as well as in physics. Okay, even in electronics. Okay, so verify the function phi of x is equal to, and this is its solution, a cos of x plus b sin x. A and b are constant, are is solution to the ODE y double dash plus y is equal to 0. Okay, and x very so the real number. Okay, so what we need to check, that phi satisfies this given differential equation. It's a second order differential equation, so phi should be definitely differentiable at least twice. So phi of x is given in this way. Let me check what is phi dash of x. I need to differentiate this twice and need to see whether it satisfies the given differential equation. So that is same as minus a times sine of x, derivative of cos is minus sine, plus derivative of sine is cos, so plus b cos of x, and again if I differentiate this function once, that is differentiating the given function twice, I get derivative of sine is cos, so minus a cos of x, and the derivative of cos is minus sine x, so minus b sine x, so I get here minus of a cos of x plus b sine of x. Okay, so that is same as minus, now see phi is given as a cos x plus b sin x, which we are repeating, so this is same as minus phi of x. So we see that phi double dash plus phi is equal to 0. Okay, and so it satisfies this given differential equation, so we can say that it is a solution to the given differential equation. Okay, now since we have already generalized the differential equation of nth order, let me write down the general form for the first order differential equation, which is obviously derived from the generalized form. Okay, so the general form of first order differential equation, ordinary differential equation, is given by, Okay, now if I write it in that form, then it is going to be an expression f of x. It will contain independent variable, dependent variable. Since it is a first order, we will have only the first derivative equal to 0, x belongs to j. Now this would be one way of writing it. Okay, now same way explicitly can be written as, we know that this is a equation containing only the first derivative of dependent variable. Okay, so I can write down this as dy by dx, and the other side can be anything in terms of x and y. I am already writing dy by dx over here. So this would be, say, some f of x comma y, okay, where x belongs to, say, some j. So this would be the another way. Okay, and how the solution would be, so any function y equal to phi of x which satisfies either this or this, so phi of x comma phi dash equal to 0 is a solution to 1. So if it is in this form, then it will satisfy d phi by dx is equal to f of x comma phi. So this is simply the general form of first order differential equation, and in this chapter we are going to discuss the first order differential equation. Okay, so the expression, the equation only consisting of dy by dx, okay, I mean x independent variable, y and dy by dx. Okay, now our main aim over here would be to solve the first order differential equation, that is to find the value of the unknown function. Okay, and we are going to discuss this in the next class, maybe some few methods in the next class of this course. Okay, thank you for watching and have a nice day.